Professor Julia. Good soul to everyone. Davi Souza here. I am an electrical engineer student at Federal University of Rio Grande do Norte. And today I will be presenting about how would be a power station in a future habitat on Mars. This is mission 72 of Habitat Marte. And it's a pleasure to be here sharing with you this amazing content. So these are the topics. Let me see if I can take it this part off. Okay, I will continue. These are the topics that I will be covering during my presentation. I will be talking about how would be a possible design for the power station, also the technologies and resources, and how would be the management of this station. And I will be talking about the protocols and also about the spin-offs and technologies that could be applied here on Earth. So my initial considerations are commonly bring this concept that was taken from this paper called Minimal Number of Settlers for Survival on Another Planet. And as you can see here, we have a pyramid. And for all of the systems that would be operating in a future space habitat, we need to consider these spheres. So in the bottom of the pyramid, we have the energetic and the industrial systems. And with that, with the building, we will be integrating a whole ecosystem composed by the atmosphere, by the ground, the water, and the living organisms. And in the top of this pyramid, we would have the human factors because we were still dealing with humans. And so this is, I believe that all of these aspects, the building, the energetic systems, and the industrial systems, and the whole ecosystem need to consider how it would be increasing the human well-being, how can we enhance the safety and also safety at all for the humans in the habitat. Considering the internal design, this is a master plan proposed by Ashhatud during the mission 47. And as you can see here, the proposal for the power station, we have the other facilities, but mainly for the power station would be integrated with the MOXIE system to generate oxygen, also a solar farm, and I'm considering here the integration with an Algae park, just in case of dust storms, because the solar farm will not be so feasible in these situations. And also, I'm considering the 1 kilo power nuclear for the whole energy generation system, and more related to the logistic aspect of this location of the power station. As you can see here, we have the most near the other facility most near of the power station, we have the engineering facility. So in this case, we can consider the logistic approach for development of technologies, integration of technologies, development of new technologies, of new solutions, and also maintenance and repairments if necessary for the systems and the other structures. As you can see here, another picture of the concept. And so, considering the internal design, I'm considering here that all the facilities will have a circumference shape with 8 meters of diameter and 3 floors. And this facility, we need to provide the basic needs, the dormitory with beds for the astronauts, a small kitchen, a dining room, a toilet, entertainment area, a food microproduction module. Considering these basic needs, like if we are considering the situation of a threat of a virus and that the astronauts will be isolated in each facility, we need to provide them the basic needs for for their isolation period. And more related to the power systems at all, I'm considering a monitoring area of electronic systems and for about the power management of the other facilities, a battery storage area that I'll be calling the battery hub, and also the alternative generation units. As you can see here in the proposal of IASH, we have the concept with the structure of 3 floors. And for the ground floor, we would have a social entertainment area, also considering the sleeping and the basic needs, the sleeping, toilet, and kitchen. More the basic stuff for the astronauts in this ground floor. In the first floor, I'm considering some photovoltaic reactors, more specifically using algae, microalgae, more specifically for energy production, but also we can have, we can produce, among biofuel, we can produce food and oxygen too. Also the monitoring area and the protection systems. And in the top, the battery hub. And I'll be explaining with more details why I'm putting the battery hub in the top of the structure. So the applied technologies for the operation, the electrical power subsystems, they will be responsible for the general systems, such as the life support system, environmental control, in situ resource utilization, and other technological systems. And this energy will need to be generated, not only generated, but also well stored. And I would consider here some support technologies like automated systems or even artificial intelligence for optimal operational procedures and data collection, detect failures, provide the balance of energy, and also take protective measurements. In these monitoring systems, there will be the goal of the systems would be to have data about the power statistics, how the power is flowing in each facility or for each equipment or technology, the quality of energy, detect faults over voltage, over current, short circuits, atmospheric discharge, really common during the dust storms on Mars, and also energy fluctuations in case of equipments more with a higher load that will be affecting the whole grid. And other equipments status like the batteries, the circuit breakers, the fuses, transformers, converters, and inverters. Considering the technologies for the operation, the first of all, as I mentioned before, the artificial intelligence, more for energy forecasting, and also to provide the reports. As you can see in the right picture, we can considering for artificial intelligence model, the numeric weather forecasts, weather data of the environment, the measurements of the environment, and also historical data of the energy production, the previous production. And we would have some modelings that will be possible to use and to provide the forecast for, as you can see in this picture, we have 10 days, but we can have maybe more days. Also, the monitoring of system parameters throughout a dashboard, as you can see in the other picture. Basically to have the flow of the energy of each system, of the whole system, of the generation, how much energy is generated, considering the forecast, we can have like an idea what energy that we are expecting and if it was possible to achieve or not. And also the other measurements about temperature, about the weather at all. And this would be providing a more fast maintenance and also accelerate team productivity. And in case of repair, the workload of the astronauts will be less. And we would have like a power plant monitoring area considering these technologies. And other solutions, I bring here for the solar farm, some concepts using photovoltaics. The first one is the building integrated photovoltaics. As you can see in the right picture, the right top picture, the cells are integrated into the building, and this would be like maybe useful for the habitat, to be covering the habitat, also protecting from radiation, but also generating energy at the same time. The malleable photovoltaics, it's commonly the same, but we have this idea with these malleable photovoltaic cells, OPV, that it's organic photovoltaics. So there is the possibility to produce organic cells to be integrated in the buildings. Also, heliothermic systems using the water heating, and also the solar or technology that consider this technology consider a honeycomb photovoltaics. So as you can see in the right bottom picture, how would be a building integrated with this honeycomb photovoltaics. We would have small cells that will have like a kind of a glass that will be directing all the sunlight, all the radiation into the cell, and will be enhancing the energy production. Also, the solutions, the tracking systems, as you can see in the right picture, just to track how is the optimal positioning of the cell to collect the most sunlight, the most amount of sunlight and radiation. And also the other solution would be the captation by central tower can be solar radiation or thermal at all. As you can see, we would have a receptor that the photovoltaic cells would be directioning, with reflectors, will be directioning all the sunlight into this receptor with a focus. And if we have like using thermal energy, we would have water flowing through it, and this water will be heated, and we would generate pressure, and we'll be rotating a turbine and generating energy. And considering the issues caused by the dust storms, as you can see here, these pictures of the Spirit rover, Mars rover. After some days, some sols, as you can see, the solar panels of the rover was almost totally covered by sand. And as you can see in the graphic, we have the amount in the yellow line, the amount of water of watts generated per hour, and the blue one, it's the tau measurements. The tau measurement measures the opacity of the cells. So as you can see, after some cells, this tau measurement got really high, maybe due a dust storm that could be happening, and the amount of energy generated decreased a lot. So these are one issue that we need to consider, not only for the rovers, but also for the whole habitat, because the solar panels would be the more feasible and viable way to generate energy on Mars, but we have these issues that we need to consider other solutions. And just bringing the idea of the rover, the recent rover to Mars, the Perseverance, is using a thermoelectric generator, using this idea of a radio isotope power system. And this power system produces a dependable flow of electricity using the heat of plutonium radioactivity decay at its fuel, and it produces an amount of 110 watts. And it will be, after some years, it will be decreasing a little. And also we'll have the Perseverance have lithium ion rechargeable batteries to meet the peak demand of the rover activities. And when we want to deal with the dust storms, we have two solutions. The first one is already implemented here on Earth. As you can see in the left picture, the automatic photovoltaic cleaners. It's a common robot structure that works independently and has a water tank, or even could provide a jet of air to remove the dust waste and wash the panels. This would be great considering the jet of air, because if we have to use less water on Mars, this would be the best solution to clean the panels, and also to not have the astronauts going outside the station and cleaning it. And the other solution here that I found is the use of wind energy. I thought this was really interesting, and a really interesting approach, because if we consider during the dust storm that we have rates of wind speed of 17 to 30 meters per second, as collected by the Viking lander, it would be a turbine of 40 meters high, would be producing an amount of maximum 300 kilowatts. So this is a great amount of energy. But if we consider the manufacturing barriers to Mars for now, maybe it won't be so feasible. It would be more necessary a small structure, and also the materials that would be delivered, or maybe, so there are many considerations to have this solution achievable to a future habitat on Mars. Just to have an idea, considering the size of the structure with like a starship. And for now, the most achievable, feasible, and more reliable, I can tell you, solutions that NASA is working on it is the CRUSI solution, or the low power reactor. Using this Stirling technology, was designed to be safe, long-lasting, reliable, scalable, energy efficient, and compact to fit inside the rockets, considering the payload issue. And the NASA tested a small prototype of this technology that generated 100 watts. And this structure can be scaled to 10 kilowatts or even megawatts. So as you can see, we could provide a lot of energy with using this kind of technologies, maybe a farm of it. And just to have an idea, it uses a titanium radiator to heat these sodium heat pipes, and also reacting with this uranium core. And for the battery hub, and considering for this area, not only a power storage area with the batteries, but also batteries, heaters, and radiators, because if we consider that the batteries have the chemical materials inside of it, the cold nights on Mars, the low temperatures will be probably an issue, a problem for the batteries. It will be affecting the well functioning of these materials, of these chemical materials, and that's why it would be necessary to have heaters and radiators on the structure. Also, a capacitor bank specifically for corrections on power demand, and it can be also useful. This device called FACT devices. Just to have an idea, it's kind of a system that use an optimization algorithm When the power demand is increased, with the whole grid will have unstable operation, and then these effects start to reduce these oscillations and these harmonics that we call the most when it happens. And so this will be deriving optimal solution to provide the voltage stability with low costs. And battery recycling, this is a big issue because, as I mentioned, we have the chemical compounds of the batteries, and maybe after a while they won't be useful anymore. So it will be necessary to have any kind of solution to recycle these batteries and this stuff. And also inverters and converters to provide the AC-DC conversion. Alternative generation units, as you can see here, the electromagnet floor that could provide that each one we call electro-IMA. I don't know if this is the term in English. And each one of these would provide an amount of 5 watts per step. Also, the microalgae, as I mentioned, as a biofuel. Also, mechanical energy of treadmills, as you can see in the left picture. Just a system, the idea of a system, electrical system to generate energy with the bicycles. And also, I saw recently this solution that is really interesting if you consider in the sanitation center, an integration with the sanitation center, the wastewater facility that would be converting also energy, that would be providing energy, as you can see in the right bottom picture, that using sludge and wastewater, we would provide not only the gas, the biogas to generate energy, but it will be also possible to provide this state to use as a soil enhancement. So to have some compounds to be used in the greenhouse. And as I mentioned, the algae cultivation with photobioreactors, as I mentioned previously, is edible biomass. We can provide biofuel, also CO2 to O2 conversion, and effluent treatment. And in the right picture, you can see some approaches of NASA integrating these green technologies with space, a lot of applications. And also I found this other solution, very interesting solution, that's called algae-powered fuel cells. That is a biophotovoltaic cell with a power density of 0.5 watts per square meters. So it's possible to have a photovoltaic cell with made by algae too. And the MOXIE, these are more resource generated in situ with the algae too. The MOXIE will be the system that will be providing the oxygen for the whole structure. And it was a prototype, a small prototype, as you can see in the top picture. A small prototype was sent to Mars in the Perseverance. And recently we have the news that they have produced the first amount of oxygen made by CO2 from CO2 to O2 conversion, taking out the 90%, taking out the carbon dioxide of the Martian atmosphere, which has an amount of 96% of CO2, and throughout solid oxide electrolysis, we will be providing the O2. And related to the management, as I mentioned, I will be talking before everything in this picture, the idea of the battery hub. So I have this proposal for the grid, how the grid would be interconnected. And on the power station, we would have like the main systems, and the battery hub will be, I'm considering this that I call emergency decoupling. So the battery hub is an area that everything can happen. We have chemical compounds, we have a lot of energy, of power, and also maybe the idea of recycling the batteries, maybe it happens something with the chemical compound. So at all. There are many possibilities if we have like a short circuit, and if something happens, maybe it will be starting a fire or something really bad, and to not compromise the whole structure and the other alternative generation units and the other systems, the protection systems. I'm considering this because we would have like a kind of this decoupling. We would have like taking out the battery hub from the power station, and just to like in case of fire, to avoid the fire, like opening the structure and so let the fire goes out. In case of like a big situation, emergency situation. And so in the battery hub, we would have the power control and the recycling area of the batteries. And in the whole power station, we would have the connection of social, food micro production and sleeping area, and also the connection with the photovoltaic reactors, the monitoring area, and the protection systems. So the ground floor and first floor, and the third floor in the bottom. The organizational structure, these will be connected infrastructures, also between the engineering center, allowing redundancy systems, more specifically with the protection systems. Like it would be interesting to have not only one area for the protection systems on the power station, but also on the engineering center would be great, because if we have a big problem, a big issue on the power station, we would have the other protection systems to not allow this failure go spread for the whole other structures. The professionals will be capable to conduct experiments aimed at grid structure or system maintenance. Some specific research related to energy systems would be done in collaboration with the engineering center, and related to the waste management, we would consider the analysis of what was discarded, the equipment recovery, reuse logistics, and disposal logistics. I'm considering here the positions, profiles, and duties. Two permanent positions that would be the power manager and the chief engineer. The power manager will be responsible to conduct the good practices awareness, not only on the power station, but with the whole habitat. Also to develop monitoring and maintenance schedules. And the chief engineer will be responsible strictly qualified professionals to conduct in situ activities, like if happens something in the crusty technology, in the kilopower, he would be responsible to go there on the installation, to go on the equipment and conduct the maintenance routine. And also to install other equipments in the other structures, electrical equipment. Some functions to be engaged: the head of the structure, the sub-chief, the analyst and maintenance. So this would be like switched between both. The duties of the chief would be more related to delegate the functions, give instructions, establish schedules, and promote the rotation between the respective center and the other infrastructure of the habitat. And this idea is more like to provide a kind of, if we have like the rotation of technologies, to test some technologies in other infrastructure, and like if necessary to conduct any kind of activity, that would be like the case of the isolation, some activity that will be not possible to conduct in the health center. The chief would be promoting this knowledge spreading, like something like this. For the astronaut training program, I'm incorporating some basic features just to have an idea of a sustainable human presence in space, as I previously mentioned, the algae, the alternative generation units. This also would necessary to conduct to have the idea of to support the long-term effects of isolation, mental health aspect, and practices to reduce costs and technical risks in overall systems, not only for energetic systems, but in the whole systems. Courses focused on basic understanding of handling and maintenance of the electrical systems. As I mentioned before, in case of something happen on the health center, like maybe a person, an astronaut over there, would be able to conduct any kind of simple activity with the electrical systems. Analysis of risks and failures, allowing the generation of monitoring reports of the systems, meetings for crew decision making, new skill to overcome emergencies based on situations identified on Mars, and simulations. This is really interesting because we don't know what to expect in the future on Mars. The astronauts, maybe what we think now about Mars, maybe when the astronauts arrive there would be totally different. So this idea of resilience, conduct simulation, generate new skills, this is really important, not only on the engineering aspect, but the other professions. Some videos, I bring here the video of the solar technology with the honeycomb, also about the kilopower, the MOXIE, and this is the Ecopia E4 robot. That was that robot that I mentioned for cleaning the photovoltaics. And also I find this really interesting video about generating power on Mars. That was from NGO, National Geographic. And just to mention, it's a really short video. If you have the opportunity, I really recommend it to see. With some thoughts of Robert Zubrin and other scientists of the area, and talking about the power generation. And just to see some pictures of the video, like as I mentioned, the reflectors, the solar reflectors, and also this really interesting idea of the solar panels. It's like the portable solar panels. As you can see in the left picture, we have the beginning, like it's almost closed, totally closed, and it starts opening and begins and stays like in the right picture. Really interesting if you consider the payload, the area to send these technologies on the rockets. Considering the energetic needs, now I'm talking about the resource need for not only 1 week, but related to the energetic needs, I'm considering that the dimensions of the energy supply, water supply, heating, and air conditioning systems will be determined by the number of inhabitants and the amount of vegetation of the environment, so the ecosystem. And according to James Reactor, which is a NASA associate administrator, he considered that for the surface to have the necessary power for the surface of Mars, for habitat on Mars, would be an amount of 40 kilowatts for the whole habitat. And as I mentioned previously, if we have like the use of solar panels, if we have the crusty, the kilopower, and the alternative generation units, we can achieve this amount and even with even higher amounts of energy supply. And so related to the basic needs, consider the number of 2 astronauts. Food, if we consider the diet and the amount of food, this will be determined by each individual, by his weight, his biotype, his routines. So, but I'm considering here an average of 2.1 kilograms per person. And for 1 week, and for 2 persons, we have an amount of 40 kilograms. Also related to water, I'm considering here 3 liters of water by person and a week consumption of 42 liters of water. Important to say that if these are the amounts, the numbers that we consider for here to us here on Earth. So on Mars, it could be different. We have maybe less water, maybe more food, we don't know. But the situations that we'll be facing on Mars will be totally different. Guidelines will be provided to other facilities. The power station will be providing indicators of consumptions and control of energy use, economy practice to be added to the astronauts' routines, basic guidelines and training for handling and conduct preventive maintenance of the electronic equipments. Also, smart reports capable of establishing the correlation between the variables of the systems to maximize the energy efficiency, and also protocols for energetic guidelines and warning about failures and emergencies. Now, related to the protocols, as you can see here, a specific protocol for the facility. I'm considering the track system notification related to deviations and irregularities, and we would have a remote monitoring for the vital systems, such as the life support systems and the environmental control. And as you can see, we would have some controllers that would be integrating the grid, the generators, and the batteries. To be delivering the amount of energy, like for the infrastructures, for loads, and for also to control the protections. And we would have like the notification if we have this, to have the status of some equipments, of some loads of the protection system. And so this would be the main aspect related to it. And with that, with this controller, we would be providing a machine operator interface with system status. Some protocols of safety, fast isolation procedures. In case of failures, faults, short circuits, lightning strikes, common sandstorms, start the emergency decoupling. Like just in this case, we would have like only the emergency decoupling on the grid, not affect the other systems. And also protection equipment, see how we'll be operating the protection equipment, and will be sectioned the generation plants from the habitat. And all of these would be activated to avoid the widespread losses. And the people in the structure will start the process of checking the status of the protective equipments, first of all, to see if any, if the occurrence, the failure affected in other specific area. And if necessary, establish in order to deactivate the generation plants and activate the bank of generators and backup batteries, the alternative generators and backup batteries. Other protocols would be about system recovery, to conduct some AVAs to monitor and assess the affected site and perform the inventory of losses and recovery schedule, and guidance more related to inform other mission members about the maintenance and repair of the energy resources. Protocols of occupancy and entertainment, as I mentioned, the human factors at the beginning of the presentation. It's interesting to have like a kind of approach to alternate the monitoring routines, not have only one astronaut conducting it, doing it. So while one will be more conducting more hands-on activities, the other one would be conducting the monitoring routines, and it can be switched. Also, socialization practice proposed by the health center, relaxation areas, physical exercise, games, and other operational activities involving the cultivation of food and interaction with plants, with this small model of production, the food microproduction model. And for this model, protocols, the main protocols of this module is more related to ensure features such as food logistics, risk management, avoid risks, and also conduct some prevention activities, prevention tasks, and provide monitoring reports, and also the waste management. And as you can see in this picture, in this right picture, it was taken from the paper made by me and Professor Julio that we presented last year on the IAC. That's called Agriculture in Mars, Habitat Marte Findings. And during the operation of the biohabitat greenhouse, the greenhouse of Habitat Marte, we had some outcomes more related about how would be the management of the structure, the routines, the general, the routines, the management, the maintenance, recycling practices, harvesting and processing. And some activities that we developed during these routines was analysis, diagnosis, ensure the circularity, also assure the fidelity of the methodologies that we would implement, that we were implementing, and also orientations and detect possible failures during these routines. Now related to the 3D printing, some protocols, and also I bring here more solutions for 3D printing that can be used with this technology, like considering the cooperative work between the Powerstation and the engineering center. It will be able to provide to develop eco devices, organic electronic devices, equipment coverage shelters, as you can see in the right picture. In the left one, also have some conductors and filaments, just to have an idea how would be a 3D printed conductor or filament. And there's another one related to microalgae. I thought this was really interesting discovery. It's like they are producing microalgae. They are printing microalgae with this bacterial cellulose. This is a novel bioprint technique to print the microalgae into a material, as you can see in the picture, in the right picture, capable of photosynthesis. And this material also is a sustainable living material because it's degradable and it's recyclable too. And also allow the production of energy, of oxygen. And this is really interesting, also considering that the algae will be producing energy and these other solutions. And if you want to go further on this topic, the reference 7 is the studies that they have conducted with this solution. And also the organic photovoltaics, the PV cells that I mentioned in the beginning of the presentation. It's a solution that has low cost manufacturing, an amount of 50%, have abundant materials, also provide the flexibility, low weight. If we consider the payload, this is a good outcome, and also proper disposal and the possibility to be 3D printed. And just to have an idea, the 3D printed solar panels are 20% more efficient than traditional ones. So also a great solution using the 3D printing that could be useful even like if on Mars the habitat already have the 3D printers, it will be easily developed this kind of solutions. Now related to the spin-offs, technologies and outputs that could be applied here on Earth. The idea of self-sustainable electricity, the most general aspect and approach. We would be providing structure with efficient resource saving. As you can see in this right picture, that the roof of this building has like solar panels that are more like a window, and provided that the light comes in and at the same time generate energy, sorry, and this would be the idea of eco-friendly environments. Also, we would have the livers with lowest possible handling and better performance for that we already call the smart grids, and the environmentally friendly technologies with carbon footprint reduction. And just to have an idea, each square meter of the OPV avoids the emission of 120 kilograms of carbon dioxide per year. So this is a really interesting solution if we consider the current situations of climate change. Some guidelines would have a sustainable energy production, creative ways to deal with solar energy issues, development of new technologies and systems to improve safety and reliability of the energetic systems, easy assembly, maintenance, and all of these with optimal procedures, solutions to keep the confidence related to control of power and its protection systems, reuse of materials and recycling practices, energy consumption management, and investment in research in different ways, adding positively to the global energy matrix. And considering now the SDGs, I bring here the most the SDGs that are more related with what I presented here. The SDG 7 about affordable and clean energy, SDG 8 about decent work and economic growth, 12, 9, and I believe that the most important one, the 13 SDG is about the climate action. And as I mentioned previously, this idea, the current situation that we are facing, these technologies, the idea of Mars exploration, of space exploration in general, could provide to us good solutions to overcome these situations. We need to have the idea that it's not only about go to space and start another settlement and a society over there on Mars, but also we need to take care of our planet, and the idea of space exploration can provide us excellent and amazing solutions that to face and overcome the main issues, the main change in this kind due to the climate change. These are my references, and thank you very much for your attention. This is my email. If you have questions, don't hesitate to ask. If you want, and if someone will be watching this video in the future, feel free to ask me if you have questions by email. Thank you very much.